Alright, so in this video we're going to finish up doing calculations involving ideal gas, and then we will be done with the second half of this thermal physics unit. Okay, so before we get into the very last part of the notes, let's do a quick question. So this question is from a past IB exam, and the question says, the equation of state for an ideal gas, PV equals nRT, describes the behavior of real gases, and then there's four answer choices A, B, C, or D. Okay, so I want you to pause it here and try to answer this question on your own. Okay, so the correct answer to this question is A. The ideal gas equation describes the behavior of real gas at low pressures and or at large volumes. Okay, and so the difference between an ideal gas and a real gas, and when I say a real gas, I mean, you know, literally like a real gas. If you take any gas and give it the correct circumstances, then you can treat it as an ideal gas. And if you treat it as an ideal gas, then the equation PV equals nRT like describes the behavior of that gas. Okay, now this equation only works provided that you're able to ignore the electrical forces, the interactions between the gas particles. And so in an ideal gas, one of the big assumptions you're making is that there's no interactions between the gas particles aside from the collisions they have with each other. And so that means for this type of question, you need to be thinking, under what circumstances would the gas particles be far enough apart from each other that I can safely ignore those electrical forces or those electrical interactions. Okay, and so that would be at low pressures where they're not colliding too often, or if you have a big enough volume, if you have a big enough space, then the gas particles as they're flying around wouldn't be close enough to each other to interact with those electrical forces, and therefore you could treat it as an ideal gas. Okay, and so that's why the correct answer is A. All right, pause there if you need to look at it some more. All right, so the very last thing we're going to talk about in this unit is the idea of calculating the average kinetic energy of a gas particle. Okay, so if you have an ideal gas, one of the properties of ideal gases is that ideal gases do not have any internal potential energy. And the reason for that is, so internal potential energy has to do with the intermolecular forces between the particles making up an object. And so in a solid and a liquid, those particles are held together by these electrical forces, right? Obviously, like in a solid, they're held together really tightly in a nice, like organized fashion. And in a liquid, they're held together, but not as tightly. In an ideal gas, the particles are completely separated, and we're making the assumption that those gas particles are flying around and not interacting with each other than through collisions. Okay, because the internal potential energy of those particles comes from those interactions, it comes from those intermolecular forces. If we assume that those intermolecular forces between the gas particles don't exist, that means that there is no internal potential energy for an ideal gas. Okay, and so when you're talking about an ideal gas, remember internal energy, it has like an internal potential energy component and an internal kinetic energy component, and we're making the assumption that the internal potential energy is 0 for an ideal gas. Okay, uh, meaning, by the way, that if we want to calculate the internal energy of an ideal gas, that energy would consist only of the kinetic energy of those gas particles. Okay, now I state this without proof, but there is an equation that allows us to calculate the average kinetic energy for a single gas particle. Okay, and here is what the equation looks like. The equation is EK with a line over it. The line over it represents average value. Okay, so we know EK is kinetic energy with the line over it, that's average kinetic energy, and this is the average kinetic energy of each individual gas particle. Now, I will point out, by the way, it is an average value because if you have like a gas, like a container full of gas, each gas particle is going to have a different kinetic energy, of course, because they're all like in random motion. Okay, so this is for the average kinetic energy of a single gas particle. The equation looks something like this. It's 3/2 times Kb, where Kb is a constant known as the Boltzmann constant. The value for the Boltzmann constant is approximately 1.38 times 10 to the negative 23 times the temperature of the gas in Kelvin. So I've said this before, but when you're doing an equation that has a T in it, the T must be in Kelvin. If it's delta T, it could be Kelvin or Celsius, but T temperature has to be in Kelvin. And so this would be the temperature of the gas in Kelvin. Right, so 3 halves times kb times T. Right, in other words, as long as you know the temperature in Kelvin of the gas, you can find the average kinetic energy of a single gas particle. Now, what does that have to do with the internal energy? Well, let's say you have like 1,000 gas particles. If you know the average kinetic energy of one, then all you would have to do is multiply that average value by 1,000, and that would represent the total kinetic energy of all of the gas particles, which would be the definition of internal energy in that case. All right, so make sure you have this equation down, and we'll do some simple calculations with this concept. Okay, so let's take a look at this calculation right here. So this question says 2.5 moles of hydrogen gas is contained in a fixed volume of 1.25 cubic meters at a temperature of 175 degrees Celsius. The second I see this, by the way, I'm thinking, well, if I'm doing any type of calculation with temperature, that needs to be in Kelvin. Okay, so right off the bat, before I even look at the problem, I'm just going to take care of that conversion real quick. I add 273 to that, and I get 448 Kelvin. Okay, now question A says, what is the average kinetic energy of each atom in the gas? Okay, so that's going to use the equation that we just learned about. EK average is equal to 3 halves times KB times T. And so that would be 3 halves times 1.38 times 10 to the negative 23 times the temperature in Kelvin, which is 448. And so in my calculator, I'm going to do, let's see, 1.5 is 3 over 2. So 1.5 times 1.38 times 10 to the negative 23 times 448. Okay, and the number I get for A is 9.3 times 10 to the power negative 21 joules. Okay, now that seems like a small amount of energy, and it is, but remember there's, a bajillions of atoms in this, in 2.5 moles of hydrogen gas. Okay, so each one might have a tiny amount of average kinetic energy. B says, what is the total internal energy of the gas? So again, if we're assuming it's an ideal gas, then we're assuming that there's no internal potential energy because we're making the assumption that the gas particles don't have those intermolecular forces between them. Okay, if we make that assumption, then the total internal energy is just going to be the sum of the kinetic energy of each individual atom. But since we already have the average of a single atom, all we need to do is we need to multiply that by however many atoms we have. So in other words, this is the average kinetic energy for one atom. If we just multiply that number by how many atoms we have, then that would be the internal energy of the gas. Okay, so how many atoms do we have? Well, we have 2.5 moles, and so, 2.5 moles, we know that 1 mole of anything is equal to Avogadro's number. Okay, so 1 mole of hydrogen is going to be 6.02 times 10 to the 23 atoms. Okay, and I can do that calculation easy enough. 2.5 times 6.02 times 10 to the 23 is 1.505 times 10 to the 24 atoms. And so the internal energy for B would be 9.3 times 10 to the negative 21, okay, which was the average kinetic energy for a single gas particle, times the number of particles I have, which I just calculated. Okay, so when I multiply those numbers together, let's see what I get. 9.3 times 10 to the negative 21. Okay, so I get 13,996.5 joules, and that is the total internal energy of the gas. Okay, so about 14,000 joules. So pause it there if you need to look at that some more. Okay, and then part C is asking what is the pressure of the gas at this temperature. Okay, so pressure with what we're given, I'm going to assume that this is probably going to involve the ideal gas law because we have the number of moles, we have the temperature, we have the volume, and so I know PV equals nRT, and so P would be nRT divided by the volume, and so that would be 2.5. R is the gas constant, that's 8.31. T is the temperature, again, the temperature in Kelvin, must be in Kelvin, divide by the volume, which is also given in the problem as 1.25. Okay, so 2.5 times 8.31 times 448, and then divide by 1.25, I get a pressure of 7,446 pascals. Okay, and so that is the answer to part C. So pause it there if you need to look at that some more. All right, so I'm going to erase this, and you're going to try to do one of these on your own. Okay, this is just the work for the problem that we just did. Okay, so take a look at example 2. I want you to try to enter example 2 on your own, and then we will be done with this video. Okay, so example 2 says a container holding an ideal gas under a pressure of 250 kilopascals is measured to have a temperature of 300 degrees Celsius and a volume of 2 cubic meters. And you're asked 3 different questions. So I want you to pause it here, try to answer example 2 on your own. Okay, so right off the bat, I see that I'm given the pressure of the gas. I'm given the temperature, although the temperature is in Celsius and I need it to be in Kelvin if I'm going to be doing any calculations. Okay, so I'm going to do 300 plus 273, which is 573 Kelvin. And then the volume is 2 cubic meters. Question 1 says calculate the number of moles of gas in the container. That is going to be an ideal gas law calculation. And I'm just going to find N. That would be PV divided by RT. And so this should be a simple calculation. 250,000 times the volume, which is 2, divided by R, the gas constant, which is 8.31, and the temperature, which is 573. Okay, so 250,000 times 2, divide by 8.31, and then divide by 573. Okay, and I get 105 moles of this gas. Okay, and so that's the answer for the first question, 105 moles. Now the second question says calculate the average kinetic energy of each ideal gas particle. So that's when you would use EK average equals 3/2 times KB times T. And so 3/2 times 1.38 times 10 to the negative 23 times the temperature in Kelvin, which is 573. Okay, and so I'm going to do 1.5 times 1.38 times 10 to the negative 23 times 573. And I get 1.19 times 10 to the negative 20 joules. Now that is for each individual gas particle. And so for the final question, the internal energy of the gas, because it's an ideal gas, the internal energy has no internal potential energy component. And so the internal energy is purely the internal kinetic energy of the entire gas. And so I need to multiply this value by the number of gas particles that I have. Well, I have 105 moles, and I know that 1 mole of anything is 6.02 times 10 to the 23. That's something. Okay, so if I have that many particles, then I can find the internal energy by just doing 1.19 times 10 to the negative 20 times the number of particles, which would be 105 times 6.02 times 10 to the 23. Okay, and so I'm going to type that into my calculator, and then we will be done with the problem. Times 105 times 6.02 times 10 to the 23, and I get a big number, 749,740 joules. Okay, and so that is the internal energy of the ideal gas. Okay, so pause there if you need to look at that some more. Okay, so we are officially done with the notes for this unit. I would highly encourage you to finish working on thermal physics worksheet number 6 on your own. As always, please let me know if you have any questions. Unless I'm mistaken, this is probably going to be the last video that I make as far as notes go for the school year. It's been a pleasure having you in IB Physics 1 for this year. I hope you have a good rest of your school year, have a good summer, and again, please let me know if you need any help or have any questions about anything. Have a great day.